of the classes are not being maintained. So the recordings are stored in Teams, but I think they last for 20 days. Okay? About the classes from March, I don't have still confirmation, but I mean, it's question of hours. Question of code examples. I think it's better that to postpone these questions to the lab session. Or if you are, I mean, if you want, you can ask me about it, but not now. We can meet outside of the class. It's okay? Because is exactly that what we are going to do in the lab session. It's okay? Well, so we were talking in the last class about distance-based methods, yeah? Well, this whole week is going to be online. I don't know what are we going to do next week. I don't know, so I cannot answer any question about this now. So, but in fact, if you were having classes in the last semester, in the first semester, I'm afraid that the teaching from next week will be something very similar, if not equal, to the same semester. But I don't know now, so I'm not the person to ask now about that. It's okay? Shall we start?
Yes.
I don't know if you have any sort of questions about the what we were studying related to nearest neighbor rules. The fact of computing distances to examples in the training set, and then deciding the classification either from the lab of the closest example or through a voting among the k closest neighbors. We were showing that we can use more and more neighbors to have more reliable votings, and the more neighbors we consider, provided they are not far from the point we are asking, we get better and better predictions. In fact, you can have a look here. What we are looking at here, it's an approximation, but anyway, we were, oops, what's happening here? Sorry, I don't know what's happening. I'm having problems. I don't know what's happening. Just a minute. Sorry. Okay, now it's working. I don't know what's happening here. Okay. Yeah, we were showing here that the more neighbors we obtain, the more close the boundary is to the optimal, in this case, Bayes classifier. This is just a toy example in which we have two Gaussians, more or less like this. This is Gaussian 1, this is Gaussian 2, and the optimal boundary for this problem is something like this. And we take more neighbors and we get a boundary which is closer to the Bayes classifier. In fact, it's quite intuitive that if we take a lot of neighbors to vote, but all these neighbors are close enough to the point we are querying, then it's quite intuitive to see that this voting is quite representative of the true probability. Anyway, and in fact, we were commenting that when we increase k, usually we obtain better and better results, but there is a particular value of k usually from which the behavior of the classifiers starts being worse. Why? Because for very far neighborhoods, it happens that if this is the point we are asking in our classifier, this is the first neighbor. This perhaps is the second neighbor. This is the third neighbor. Then the k neighbor can be very, very far away. If one neighbor that is very, very far away is voting exactly as the one which is closer, then it's quite clear that the label of this neighbor is not representative of what is happening here. Is that clear?
Is it like we start to have more noise?
Well, but we cannot consider this as noise, because these points, these examples correspond to a training set that can be truly representative of our problem. We talk about noise when we have examples which are like corrupted. You know what I mean?
Yes.
We usually don't refer to that as noise. These are fair prototypes, but the problem is that you go to find neighbors too far. So when they vote, this voting result is not reliable. On one hand, you need large values of k to have a good votation, but you need neighborhoods which are very, very, very close to the query point. And these two aspects constitute a trade-off, you know? And usually this trade-off is the best and one particular value. Let's go on a little bit. This takes us to think about whether we can consider how good the k nearest neighbor rule, because the k nearest neighbor rule, it's a generalization of the nearest neighbor rule. It's okay? So let's think about how good this rule is. To do that, we are talking about the asymptotics, which means what happens when n tends to infinity. So imagine that we have as many examples as we want. So imagine a problem, no matter if it's an easy problem with two Gaussians or a very, very complex problem with arbitrary distributions. But imagine that you have infinitely many examples. It's okay? No noise, no errors. It's okay? So under this assumption, the thing is that no matter how many neighbors, for example, here we have 1, 2, 3, and 4 neighbors. But imagine that you have a very, very high number of k. If, well, let's talk first about 4 neighbors. Imagine 4 neighbors. If this is true, if the number of neighbors tends to infinity, it means that the neighborhood formed by 4 neighbors, its size, I mean this radius, is an infinitely small quantity. So the size of the K neighborhood, I think we refer to that as V K of X. Can't remember. So the size of the neighborhood, let's call it, well, it's not equal. It's proportional. It's okay. This tends to 0. In other words, the 4 neighbors are infinitely close to X. Do you agree? Okay, this is true for any number, for any fixed number of neighbors. The problem is that in order to improve the rule, we want to increase K. So we cannot increase K arbitrarily. So let's see what happens. So imagine K equal to 1. And imagine C equal to 2, because it's easy. Well, in this, imagine that our problem consists of 2 Gaussians. This is not written in the slide, sorry. 2 Gaussians. The 2 Gaussians are, or could be, for example, here, well, not exactly there, something like here and here. So we have an overlapping. That's why the posteriors have this shape. This is the Bayes classifier, and this is the posterior for class 1 and the posterior for class 2. It's okay? And our space is a 1-dimensional space. It's okay? The bias classifier works like this. Decide the class whose posterior is greater. So we decide 2 at this side of the boundary, and we decide 1 at this side of the boundary. It's okay? And this is the probability of error at X. It's okay? Let's see what happens with the one nearest neighbor. Remember that when you have overlapping, as we have in this case, can you see the overlapping here? We have overlapping here and here. It's okay? Let's see what happens. X is the point we are querying. We are moving X around this axis. And X1 is the nearest neighbor of X. It's okay? But because the nearest neighbor is infinitely close to X in the asymptotic case, okay? Then, which is the probability of error of the one nearest neighbor rule? Well, the probability of error corresponds to the fact that X is the probability of X is from class 1 and the nearest neighbor is from class 2. Because in that case, we are assigning the label 2 to X. You understand that? And, or the probability of X being from class 2 and the nearest neighbor coming from class 1. Can you see that? We could draw, for example, one case here. This is X. Okay. Let's use, for example, this is X, and this is X1 very, very close to X. The probability of error is this probability multiplied by this probability, because in this case, the nearest neighbor is taken from class 2, but the point is from class 1. But it can also happen the contrary. I mean, that this. But because we are in the asymptotic case, these two values and these two values are the same. So we have this expression. Do you agree? More or less? Okay, so if this is true, comparing this, which is just the minimum between these two, the minimum is this amount. And now is this multiplied by this plus this multiplied by this. If we integrate this quantity and this quantity over the whole space, we obtain, well, first of all, we can write this expression in terms of this expression. Well, we can relate these two expressions. And then we can write that this risk of the nearest neighbor rule is equal to the minimum multiplied by the maximum, because in this case, c equal to 2, this is very easy. Class 2 is equal to, the probability is 1 minus the other one. You see? And this expression is always bounded by twice the bias error. If we take the integral, as I was saying, we have the total probability of error of the nearest neighbor rule compared to the optimal one. So what this means? Well, this means that the probability of error of the nearest neighbor rule is bounded by twice the optimal one. This means that if I have problems with zero overlapping, imagine this problem, class 1, class 2, zero overlapping, which is the Bayes error. Anyone? Imagine a problem with no overlapping, which is the Bayes error in this case.
It should be 0, right?
0, bingo. 0. Can you tell me which is the probability of error of the nearest neighbor rule?
Sorry, can you repeat, please?
Yes. You have said that the Bayes error in this case is 0.
Yes.
Now I ask you, which is then the probability of error of the nearest neighbor rule?
I don't really know.
Well, you know that is bounded by twice the optimal one. So it's bounded by about by twice 0.
Okay.
Which means?
I don't think I get it. Sorry.
Anyone?
Also 0.
Also 0. I mean, the probability of error of the nearest neighbor rule is bounded by twice the optimal one. If the optimal one is 0, then this one is also 0. That's an important result. You see?
Yes, yes.
So
now I do.
For problems with 0 or very small overlapping, the one nearest neighbor rule is quite good, because twice something very small is something very small. What's the problem? The problem is that if I have a problem with lot of overlapping, then the Bayes error is high. Let's consider a simple example. Let's consider a simple example. Imagine this case. Class 1. I don't know what's going to happen. Class 2. You see? Class 1 and class 2. Imagine that these are the weighted distributions. So Bayes classifier is this. This. Class 1 on this side, class 2 at this side. It's okay? So the Bayes error is something like, let's do a simple example. We can develop this example in an exercise, for example, but now consider something slightly easier as, for example, this. In this case, the Bayes error is exactly proportional to that. So we can make this area small or high. So this is a case, and this could be another case. So this is a problem with high overlapping. This is a problem with small overlapping. Imagine that this is I don't know 0.3 Bayes error, and imagine that this is 0.1 Bayes error. So in this case, the probability of error of the one nearest neighbor rule has to be smaller than 0.6, which is very, very high. This is just a bound. But in this case, we are sure that using the one nearest neighbor rule, the probability of error has to be smaller than 0.2, which is a small value. It's okay? The smaller the Bayes error, the best the nearest neighbor rule is, just with one neighbor. It's okay? Well, the corresponding analysis for the k-nearest neighbor rule is much more difficult. So we are not going to develop it. I mean, I hope you have understand that, because it's just reasoning about probabilities and with the Bayes classifier. In the case of k neighbors, the thing gets more complex. But anyway, what is true is that we need to have infinitely many examples. So what I called n in the other slide. But we also need that the number of neighbors, they also have to be infinite. But because they need to be infinitely close to x, then we need to assume that the ratio k to n tends to 0. We need these assumptions in order to obtain the asymptotic result. We have infinitely many examples, infinitely many neighbors, but not as many as examples. It's okay? And with these assumptions, is it possible to arrive in the same way that we have obtained a bound like this here? It is possible to obtain a bound for the k nearest neighbor rule, a bound like that. which means that the k nearest neighbor rule tends to the optimal possible result. In fact, it is possible to obtain a plot like this, which you are supposed to be able to interpret, which says the following. This is for c equal to 2. And we have here, on one hand, the Bayes risk or probability of error from 0 to 0.5. Why 0.5? Why from 0 to 0.5?
If the risk is higher, we just choose another class.
Yeah, because I mean, is the range that makes sense, because 0.5 with c equal to 2 means random classification. It's okay? So in practice, this is the worst possible probability of error with c equal to 2 in practice. Okay? And what happens with the k nearest neighbor risk or probability of error? Okay, we are plotting here the function R star, which is the Bayes rule. So this is the identity. Okay? And we are plotting here twice the Bayes error. This line here is this bound here. You see? This line, this bound. It's okay? This curve here this blue curve here is exactly this function here that is obtained from this expression that has been obtained through this reasoning. It's okay? And the other curves corresponds to the expressions that we have not obtained for k equal to 3, k equal to 5, k equal to 7, and if we go on, then we get closer and closer and closer to R. It's okay? So in fact, the bound, let's write in blue. The bound for k equal to 1, the bound to R star, is not a tight bound. The other expression, you don't need to know it, this expression is tight. In fact, is exact in the asymptotic case. So in fact, if in the other example, when the Bayes rule was 0.3, the Bayes rule is 0.3, the probability of error of the nearest rule is that one, which is much smaller than 0.6, which is twice. You see? we have a way of bounding the probability of error of the nearest neighbor rule. And we know that the higher the k, if we have enough n, the higher the k, the better, as long as we are in the asymptotic case. When we move from the asymptotic case and we have to go and look for neighbors too far, then this does not apply. It's okay? And we also know that the closer to 0 or the closer to 0.5 in c equal to 2, the tighter the bounds. The bounds are looser, are worse around this region. This difference are higher than this difference here. Anyway, the interesting part is, of course, this part, because we always look for small values of the errors, of course. Questions? So summarizing, in the asymptotic case, when we have as many examples as we want, in that case, if we look for the appropriate value of k, the rule is optimal, as optimal as the Bayes rule. It's okay? But the problem is that in practice, we cannot assume that we are in the asymptotic case. In fact, we don't know whether we are or not. Okay? Because we don't have we cannot compute the Bayes error. If we could, then we would have solved the problem. It's okay? We can only do this for toy problems. So what do we do in practice? Well, we can do several things. We can modify the rules, or we can just use particular values of k and try to look for the best option according to the examples we have. Okay? In the literature, there are several modifications and extensions of the nearest neighbor rule. Instead of considering big neighborhoods and use a plain voting, there are proposals in the literature as the following ones. For example, what is called averaged neighbors, in which we obtain a neighborhood that can have several labels. For example, neighbors from class 1, neighbors from class 2. Then we compute the average of the neighbors from class 1 and the average for the neighbors from class 2, and then we decide according to these averages, or we can average in a different way, like this. So we compute the distance to each class and then decide according to this. Okay? This is something which is similar to voting, but perhaps in this case, well, this is not a good example. The example would have been much better if we would have put, for example, imagine that we have 1, 2, 3, 4, 5, 6, and imagine that the mean is this one. So the green mean is closer to X, but if we take the same neighborhood and we vote, we have more blue votes than green votes. So this rule is different from the plain voting nearest neighbor rule. And this neighbor, in some cases, works slightly better in practice. In some cases, not always. We can also look for neighbors not according to distance, but according to how they surround the point. So, for example, if we have neighbors like this, and we start looking for the first, second, third, fourth, fifth, at this point, the blue votes are higher than the green votes. But what do you think? We have a green class here and a blue class here. What do you think about point X? It belongs to green or to blue? Well, we cannot know, but I mean, plain voting says this X point is blue, but this X point is like more embedded in the green zone. So if we take the neighbors by considering a neighborhood, we can perhaps modify the decision. So there are several rules that are based on this example. Another modification is what we call graph neighbors. For example, we have points and we can compute distances between all pairs of points, or we can consider, we were studying proximity graphs. We can use proximity graphs to represent how the points relate to each other. Imagine that this is a, I don't know, for example, the Delaunay triangulation, which is a proximity graph. Instead of computing distances, we can compute distances on the graph. On the graph, for example, this point is at distance 1 from X, this point is at distance 1, this point is at distance 1, and this point is at distance 1. But this point is at distance 2. So we can use these distances instead of the distances in the space. And then we can compute what are called graph neighbors. These rules, if the graph is appropriately defined, can perform better in practice. Also, to cope with finite training sets, it's possible to consider weights on the examples in such a way that distances to prototypes with more weight vote more. So instead of counting votes, we are weighting votes. And this gives rise to a full family of weighted nearest neighbor rules. In the same way, is it possible to weight the distance? I mean, to modify the way in which I look for neighbors. So if distance is more complex than Euclidean, perhaps my neighborhood can have shapes like this instead of shapes like this. What's the problem? The problem is that how can we arrive to this distance? Because the only way to obtain these non-trivial distances is using, again, data. So there are several proposals in the literature to obtain this kind of distances. Okay? Other options to improve the behavior of the nearest neighbor rules in practice corresponds to processing the examples. For example, imagine that you have, as in this picture here, imagine that you have two classes, one Gaussian and one other Gaussian. For these two Gaussians, the optimal rule is the one you have here plotted in red. That one. This is the optimal classifier. But of course, you have here a lot of overlapping. It's okay? That's why the nearest neighbor rule and k nearest neighbor rule for small values of k may fail because of this overlapping. But what if we remove this overlapping? Here, as you can see, the red points on the left-hand side of the plot have been removed, and blue points from the right-hand side have also been removed. This is what we call editing. But this process is not trivial. But if you could do it, then the needed rule will give you a classifier very, very close to the optimal one. Why? Because if you remove the overlapping, imagine two Gaussians with overlapping and two Gaussians in which you have removed your overlapping. What happens? No overlapping means bias error 0 and means risk of the needed neighbor rule 0 as well. So if you could remove the overlapping, then you can simply use one neighbor and obtain the optimal result. This is the idea, but this is not easy, but I mean, this has also been proposed in the literature. And also, it is possible the following. I mean, if you have the previous problem, you know that for this problem, the optimal classifier is something like this. But could you reproduce this classifier with perhaps only a few examples? Well, for example, what you have here, you have 1, 2, 3, 4 points of class 1 and 1, 2, 3 points of class 2. And the one nearest neighbor rule for these points is this, which is different from the optimal one, as you can see. Yeah, but what if, now forget about these points. What if you have, for example, this on one hand, and this, and this on the other? What would be the boundary of the one nearest neighbor rule associated? Well, this is not correct, sorry. This, and this. Now, 1, 2, 3, 4, 5 on one hand, 1, 2, 3, 4, 5 more or less on the other hand. Which is the nearest neighbor rule now for this set of prototypes? I will tell you something like this. Do you agree? This is a piecewise linear function that is formed with only 10 examples, and that is very, very, very close to the optimal one. You understand that? So the thing is that it is possible to find a small set of examples whose decision boundary using the nearest neighbor rule is arbitrarily close to the optimal one. Now the problem is how to find these examples, because this is a combinatorial problem. That's bad news. It's okay? Questions? Questions? No questions? Okay, in the second lab session, we will be dealing with distance-based classifiers, and we will have a hands-on experience using that classifiers. But I mean, you don't need to know the exact expressions or the asymptotics, but you need to know that the nearest neighbors can be, in some cases, very, very good approximations to the optimal possible result, but they can also be bad if some of the assumptions do not hold. I mean, if you have to go too far to look for neighbors, then nothing of this is true. The other big problem of nearest neighbor rules is that they are not efficient, because all distance-based rules need to compute distances between everything, and computing distances to the whole training set can be very inefficient. Let's break. Okay, let's do a short break. Hello? Do we already have some pairs, or you need to think about it? Okay, why don't you, you can go to the teaching system. And let me open a forum. Let's call it, okay, general discussion Okay, in the teaching system. Okay, can you hear me? Yes. Okay. Okay. I have just created a forum in the teaching system called General Discussion. Please send your proposals for paintings through this forum. Can you see this forum? So while we are going on with the class, you can at the same time, if you want, send proposals through this forum so that we cannot collapse the chat here. It's okay? But I think it's a good idea that you talk between you and me. If you have already clear that you want to work in a particular pair, just send me notice to this forum. And then I will arrange everything for the next Wednesday. It's okay? And if you don't know each other, you can also talk and discuss using this forum if you want. It's okay? Remember that messages sent to a forum have a delay of 30 minutes unless you go through the advanced options and send the message with no delay. So be careful. It's okay? It's okay. We need to organize in pairs before Wednesday. It's okay? The other task is to okay. I will upload the statement of the first session when we finish the class. Okay, because I have it, but I need to. Okay. Any questions about the nearest neighbor rules? Some details. Let me show you a couple of examples that you already know, but anyway, this is you are having a look at the okay. This problem. For this problem, we have this. If we compute the nearest neighbor rule, the 3 nearest neighbor rule, and the 11 nearest neighbor rule. In this case, the data is Gaussian. This is a toy example. For this toy example, we can compute the optimal classifier. The optimal classifier is the Bayes classifier, which is a quadratic classifier. This classifier has the minimum probability of error. Okay? And now we can compute for the whole family of nearest neighbor rules for 1 neighbor, 3 neighbors, 5 neighbors, 7 neighbors. Why? even number? Well, because if we use for two classes, sorry, not even numbers, then we can have ties. So there's no point in using even numbers. Okay. So the higher the k, we are measuring the error on the train and the error on the test set. Okay. So as always, the error on the test is always an optimistic value compared to the error on the test. And you can see we have this behavior, which is in some ways unusual. Let's repeat that. Okay, let's put away this, because now you know it's the same data, just another random sample. So for a different random sample, well, things are similar but not equal. And now we have a different plot. So you now understand that with not many examples, I don't know if you are here. Are you there?
Yes.
Okay.
Yep.
Okay, so we can have different behaviors from different random samples, but always the error on the test is above the error on the train. Okay. Moreover, we are computing here the Bayes error, the theoretical one, which is this plotted curve here. This is the theoretical one, and then this is the, instead of the optimal one, we can estimate the quadratic classifier from the data. You understand the difference? And then we can measure the error from the Bayes classifier on the training test or on the test set. And then we have bounds or biased estimates of the true value. So we have this band here of what the Bayes classifier has. So in fact, we have here, as you can see, for k equal to 7 and k equal to 9, we have values of error that are below to the optimal one. How can it be? Does this mean that this classifier is better than the Bayes classifier? Anyone? Anyone? How can it be that I have a result that is below the optimal one, which is here? Could you answer? Hi. Hello. Well, the Bayes line, the optimal one is a dotted line here. Perhaps it's too thin. Let me try if I can change. Let me see if it is this one. Let's see whether this works or not. But the problem is that now it will be a different random sample. It's failed. Oh. Well, now we have another random sample. But anyway, the question remains. I mean, now you can see better the optimal rule. It's okay? And you have a result here which is below the optimal one. How can it be? How is this possible? Because this line, this orange or yellowish line, is supposed to be the optimal possible probability of error. And we have a better result here on the test. Why?
Maybe because it's overshaped. I think we talk about that in other classes.
Well, the only thing you have to take into account that this is nothing but a random result on this particular set, while this line is a probability. We would need to repeat this again and again and again and again over a large enough number of examples in order to properly estimate this probability. In fact, see what happens, because I have here 500 examples. Let's see what happens if I increase the number of examples. Let's see what happens. Now we will have to wait. Perhaps too much. Yes, perhaps too much. Let's be patient. Okay. Now we have much more. So what has happened? Now the estimates are much closer. In fact, now we should, I don't know, let me change the scale. Okay, much better now. As you can see now, again, we have an too optimistic estimate, but now we can look for a different behavior of different rules. If we repeat this again with different number of prototypes, then we can have arbitrarily different results. It's okay? This is with very, very few number of examples. So at the end, we are dealing with random estimates. It's okay? Okay, I wanted to show you other examples. But not here. Okay. We will do some of this. We will plot and show these figures in the second lab session. It's okay. The thing is that even for this toy problem, is not quite clear what the optimal value of k should be. That's the main lesson to be learned. So even in this very, very easy and controlled experiment. So which is the best value of k? Difficult to say. And even the best value of k is not representative of the real probability of error. So at the end, in practice, we should look for the best value of k. It's okay? Questions? No questions? Okay, if there are no questions, then we should move on to our next lesson. Okay, if you remember, we were talking about the basics, the Bayes classifier, the formulation. Then we introduced the distance-based methods of classification. For that, we introduced the non-parametric methods. And we were talking about two kinds of non-parametric approaches. The first kind, or the second, was using distances, and the second kind was fixing the functional form of the classifiers. Fixing the form of the classifier, if they have to be complex enough, it means that this classifier needs to have some sort of flexibility or some sort of complexity. And this means that we usually will have some parameters. And then the problem becomes into estimate the parameters of the classifier, not of the parameters of the distributions, but the parameters of the classifier. Okay? This approach leads to the more complex and up-to-date classifiers used today. But anyway, we will have to start from the beginning. And the beginning means fixing this form as a linear function. So that's why we are talking about linear. But the thing is that once we introduce the linear case, then we will generalize in many ways to the non-linear cases, which are the important ones in practice. It's okay? So let's start today with in the block called linear machines and kernel methods. We are going to talk today and next week at least about what we call perceptrons. It's okay? As I was saying, we assume a model for the discriminant functions. So we have already worked with discriminant functions. We will refer to this discriminant function as a function J. Well, in some cases we will be talking about the easier case in which we have only two classes, because in this case, instead of two discriminant functions, we have only one. Remember that? We have only one function, and then this function, the output is either positive or negative, and according to that, we decide class 1 or class 2. It's okay? This discriminant function has some parameters. These parameters are usually called weights. In our particular case, because we are talking about linear machines, our classifier is nothing but a linear function. What a linear function is? Well, we have d dimensions, dimension 1, dimension 2, dimension d. A linear function in d dimension is nothing but a set of weights applied to each dimension. We multiply each weight by each input, and then we add a bias term. Mathematically, if we write the weights as a vector, weight 1, weight 2, etc., then what we have, and then we call this input as vector x, then what we have is the inner product of the input vector to the weight vector, and then we add a bias. And this is our linear discriminant function. graphically, we will display this as in this diagram. We represent this node as a sum, and this here is the bias term that is added after we weight the inputs and sum them. It's okay? Well, in this way, this output then is used as a discriminant function, which means we decide according to this output is positive, negative, then we decide class 1, class 2. With these functions, the problem is that we can only produce for a given space, for example, for 2 dimensions. With this, we can only have linear boundaries. It's okay? Only linear boundaries. Well, linear boundaries are very limited in general. We can only solve very, very, very simple problems with linear functions. That's true. But, in fact, imagine Gaussians. Imagine our problem is a toy problem that use Gaussian distributions. We cannot solve these toy problems with Gaussian functions. Sorry, with linear functions like this. We know that. But it's very easy to do the following. Imagine that in 2 dimensions. In 2 dimensions, our linear classifier is dimension 1, dimension 2, and bias term. Weight 1, weight 2. It's okay? And then we have linear functions. But let's do the following. Let's make another input with x1 times x2 with another weight. Weight 1, 2, for example. And let's make another input with x1 squared with another weight, and another input with x2 squared with another weight. What do we have now? Anyone? Take into account that we can do that. We can always take our 2 dimensions and compute all these products and input them to a linear function. What do we have now at the output? I don't know if you are saying something or writing something. No one? Do you want me to write it? Weight 1, 1, x1 squared plus weight 2, 2, x2 squared plus weight 1, 2, x1 times x2 plus weight 1, x1 plus weight 2, x2 plus the bias. What's this function? Hello? Do you see that this is linear? This is a linear function. A linear function in 2 dimensions is this. Sorry. This is a linear function in 2 dimensions. And that's what I have when I add these 3 extra phantom inputs. This is linear. What is this? A 1? Yeah, it's a quadratic function. If I consider all possible set of 1, 2, 3, 4, 5 weights, 6. I have all possible quadratic functions. With this model, using only this part of the classifier, I have all possible linear functions, but all possible linear functions are too simple for some problems. For example, for toy problems with Gaussians, for example. But with this trick, then using the same scheme gives me all possible quadratic functions. Can you see that? In fact, I could have plotted this extension in the following way. I have 2 dimensions, then I can map these 2 dimensions into 1, 2, 3, 4, 5 dimensions, because this one is x1, x2, x1 times x2, x1 squared, and x2 squared. And these 5 dimensions can then be used to this new. And then we have the bias term here and the bias term here. So I could have used this 2-step way of doing. Anyway, this kind of, and the same I've done with from 2 to 5 for quadratic, I could repeat this for cubic or for exponential or for any other fixed functional form. You see that? I can always convert my original problem into a different space and then use this linear function in a transformed space in such a way that the resulting boundaries in the original space can be either quadratic or exponential or logarithmic or whatever. This approach is called generalized linear models or function or classifiers. The only thing is that in order to approach in this way, this generalized linear model has to be fixed. So at the end, the only thing we learn from data are the weights at this step, not this mapping. This mapping needs to be fixed, at least at the moment. It's okay? So linear models are in fact quite limited but they can always be extended using fixed mappings, so we can get functions as complex as we want, in principle. It's okay? We can use any kind of mapping as long as this mapping is fixed. But nevertheless, no matter whether I use the plain linear function or the generalized linear function, at the end, the formulation here is the same. If we call at this, we call this y, and we call this weight a, and we could rewrite this generalized linear function as a plain linear function if we define the new weight in this way and the new coordinates or dimensions in this way. Instead of having a bias term, instead of having something like this with a bias, we can always have this. This is an input at 1, you see, with no bias. You see that this is equivalent. It's okay? So in these slides, we are going to refer to our linear functions as this. And everything we say about these linear functions can be applied to both plain linear functions and also generalized models. It's okay? You are supposed to be familiar with linear functions. If not, you should carefully have a look at the expressions, because linear functions are everywhere. So you are supposed to be slightly familiar with them. In the next class, we will develop some expressions, both from the mathematical point of view and also from the graphical point of view. It's okay? W0 is a value or a vector? No. This is the bias. These are vectors. Vector, inner product vector. This is a scalar, and this is a scalar. It's okay? In these slides, I try to use bold for vectors and non-bold for scalars. Okay? So have a careful look, and in the next class that will be next week, we will go on from this point. Okay? Please send your organization in pairs as soon as you know through the forum in the virtual system. I've seen that we are having some messages already. Yeah, I have 9 messages. So please go on and send your proposals. The sooner we have the organization in pairs, then the less time we will lose in the next lab session. Okay? So see you on Wednesday. In several minutes, I will upload the contents of the lab session. It's okay? So please have a look.
See you.
Have a look at the teaching system. See you. Bye-bye.
Bye-bye.
Perfect.
Bye.
Bye.